Okay, so let's unpack this. We usually think of the internet as something out there. You know, it's in our pockets, on our desks, maybe in your thermostat if you're fancy. But today we are looking at a future where the network isn't just something you use, it's becoming something you are.
It does. It sounds like the opening narration of a dystopian movie, doesn't it?
Yeah.
But if you look at the stack of research we have in front of us, that boundary between user and network is, well, it's dissolving much faster than people realize.
Right. We're doing a deep dive into two things that seem totally different but are actually on a collision course. First, the quantum internet, and second, brain-computer interfaces, or
Yeah,
BCI.
exactly. And the reason we're pairing them is that they represent the next evolution of connection.
Hmm.
On one hand, you have the potential for a network that is physically unhackable based on quantum mechanics, and on the other, we have the technology to plug our brains, the most vulnerable device in existence, directly into that network.
Which raises the ultimate question. If we build an unhackable internet, but the device we plug into it is the human brain, what happens when the brain itself gets hacked?
That is the trillion-dollar question.
Hmm.
And looking at these sources, specifically the research from the University of Pisa and this massive study on BCI security, stakes just couldn't be higher.
Hmm.
We're talking about the difference between curing debilitating diseases and, potentially having your P9 code stolen directly from your thoughts.
So, no pressure then, just the future of human autonomy. Let's start with the infrastructure first, the quantum internet. Now, I consider myself a pretty online person, but when I hear quantum internet, I just picture my Wi-Fi router, like glowing blue and hovering. What are we actually talking about?
Well, first, we need to make a distinction that the researchers make. There's the quantum internet, which is the big, broad vision, the global ecosystem. And then there are quantum networks, which are the nuts and bolts, the protocols and the physics that make it all work.
Okay, so what's the difference between sending an email today and sending a quantum email?
So today, when you send an email or a text, anything really, you're sending a copy. You type it, your computer turns it into bits, ones, and zeros, creates copies of those bits, sends them to a server, which copies them again and on to the recipient.
Right. Digital equals copyable. That's the foundation of the modern web. If I send you a meme, I still have the meme on my phone.
Precisely. But in the quantum world, the rules of the game just change completely. The quantum internet relies on something called quantum entanglement and a principle called the no-cloning theorem.
The no cloning theorem, that sounds like a rule strictly enforced by the Jedi Council.
It's actually a fundamental law of physics. It states that you cannot create an identical copy of an arbitrary, unknown quantum state. You physically cannot clone a quantum bit.
So if I send you a message on the quantum internet,
You aren't sending a copy. You're transmitting the state of that information. And here's the aha moment. Because it can't be cloned, if a hacker tries to intercept it, if they try to observe the signal, they alter it.
they break the seal.
They break the seal. Exactly. In quantum mechanics, observation changes reality. If a hacker tries to measure the qubit to read your message, the state collapses. The message is destroyed, the noise on the line spikes, and both the sender and receiver know immediately that someone is listening in.
That is wild. So it's not just that the encryption is hard to break, it's that the act of spying destroys the message. It's like sending a letter that self-destructs if anyone but the recipient touches the envelope.
That's a great analogy. It's tamper-evident by the laws of physics itself.
But is this just, theory, or is this actually happening? Because I'm still paying for mediocre Wi-Fi that drops out in the kitchen. I don't see any quantum routers at Best Buy.
It is very much happening, just not in your kitchen yet. The research highlights that we're already in the early stages. We have something called quantum key distribution, or QKD. These networks are already being deployed via fiber optics on the ground and even via satellites in space. Yes. The MISHA satellite, for example, has been used to distribute these quantum keys over massive distances. Right now, it's mostly used for super high security encryption keys, so government banking level stuff. We aren't surfing the web on quantum yet, but the security layer is being built as we speak.
So why aren't we all using this yet? Why is my router still just a boring gray box?
Because quantum states are incredibly fragile. There's a phenomenon called decoherence. Basically, qubits hate interference. Any interference, temperature changes, vibration, stray electromagnetic fields, anything can cause them to lose their state and just turn into useless noise.
So they're high maintenance.
Extremely high maintenance. And there's another huge hurdle, the repeater problem.
What's that?
Well, think about a Wi-Fi extender in your house. It takes a weak signal, copies it, and blasts it out loud, right?
Right. That's how we get internet to the backyard.
But remember the no cloning theorem.
You can't copy the signal.
You can't copy the signal. So you can't just use a standard amplifier to boost a quantum signal over long distances. If you try, you destroy it.
Oh, wow. So you can't just boost it.
No. So researchers are racing to invent quantum repeaters and quantum memory. These are devices that can catch the entanglement, store it for a split second without looking at it, because looking destroys it, and then pass it along. It's an incredibly difficult engineering problem.
Okay, so picture this. We're building this incredibly sophisticated, fragile, high-maintenance glass pipeline for information. That's the network. Now let's talk about what we're plugging into it. Segment 2, the brain.
This is where the story shifts from physics to biology, and the acceleration here is just as rapid.
The sources walk us through the evolution of brain-computer interfaces. I always thought BCI was just, using your brain to move a cursor on a screen for paralyzed patients.
That was the 1970s. That's the acquisition phase, just reading the brain signals. But the big shift today, and what this paper really emphasizes, is that we've moved to closed-loop or bidirectional BCIs.
Bidirectional, meaning the conversation goes both ways.
Correct. It's not just the machine listening to the brain. It's the machine sending signals back into the brain. Stimulation.
So like writing data to the hard drive.
In a sense, yeah. We're already seeing this in medical context. Take deep brain stimulation, DBS. It's used for Parkinson's disease. In Parkinson's, neurons fire in this chaotic rhythm that causes tremors. The DBS implant delivers electrical pulses to specific parts of the brain to override that chaos.
It's like a pacemaker for the brain.
Exactly, or the NeuroPace RNS for epilepsy. That one is fascinating because it's a smart system. It monitors brain activity, it waits for the specific electrical pattern of a seizure starting, and then zap it, sends a counterpulse to stop it before the patient even knows it's happening.
That is incredible. I mean, that's life-changing tech. It gives people their autonomy back.
It is. It's miraculous. But we need to look at how this actually works to understand the risk. The sources break down the BCI lifecycle into 5 phases. It helps ground the magic in reality.
Okay, let's walk through that. Step 1.
Step 1 is signal generation. That's just your brain doing its thing. Firing neurons because you want to move your arm or think a thought.
Okay.
Step 2.
Acquisition. That's the electrodes, either on your scalp or implanted inside, picking up those tiny electrical voltage changes.
Then we have processing.
Right. The analog signal gets turned into digital data. Zeros and ones. Then comes step 4, decoding. This is where AI or machine learning looks at that data and figures out, oh, he wants to move the cursor left.
And finally, step 5, the application. The cursor moves.
Exactly. But in a bidirectional system, that cycle reverses. The application sends a signal, it gets encoded, and the electrodes stimulate the brain. You are effectively installing a right access port into the human cortex.
And that brings us to the core conflict of this deep dive.
Yeah.
The source material uses a specific term here that, I have to say, gave me chills.
Yeah.
Neurosecurity.
Yes. The researchers make a very, very blunt assessment. BCI security is currently immature. We are building these systems for medical efficacy, not for cybersecurity. Which leads to brain hacking. And I don't mean hacking your productivity with caffeine. I mean literal malware for the mind.
We have to look at the specific attack vectors mentioned in the report.
Yeah.
Because they aren't hypothetical scenarios for 100 years from now. Some of these have already been demonstrated in labs.
The one that really stuck with me, and this felt like something out of a spy movie, was the misleading stimuli attack. The P300 potential. Can you walk us through that?
So the P300 is a very specific spike in electrical activity your brain generates when it recognizes something significant. It happens about 300 milliseconds after you see the thing. It's a reflex. You can't control it. It's your brain saying, I know that.
Okay, so how do you weaponize a reflex?
The researchers set up an experiment where they showed users a series of images, but they flashed them incredibly fast, subliminally. We're talking 13.3 milliseconds. It's way too fast for your conscious mind to register, hey, I saw a picture.
But the brain sees it.
The brain sees it, the visual cortex registers it, and if the image is something significant to you, like your bank's logo, or a picture of someone you know, or even numbers from your PIN code, your brain fires that P300 spike.
Wait, so an attacker could theoretically show me a blur of images on a screen, maybe while I'm playing a game, and my brain would unwittingly confess, yes, I bank at Chase, yes, my PIN starts with a 4, and yes, I know that person.
Exactly. They can mine private information directly from your neural processing without you even realizing you're being interrogated. It's a lie detector that bypasses your will entirely.
That is terrifying. It's like a phishing attack, but they don't need you to click a link. They just need you to look at the screen.
It is. And that's just the passive reading side. The writing side, the stimulation attacks, are where the physical danger comes in. This is what they call brainjacking.
Brainjacking, which sounds like a bad 90s movie, but the reality described in the source is pretty grim. We're talking about physical damage.
Yes. If an attacker gains control of a neurostimulator, like the ones for Parkinson's, they could overstimulate the tissue. They could literally burn brain tissue or cause damage to the neurons. But they can also alter the parameters just enough to change the patient's state.
The source mentioned changing voltages can induce mania or depression.
Right. There have been documented side effects in legitimate therapies, where patients experience pathological crying or inappropriate laughter just because the stimulation was slightly off. Now imagine an attacker doing that on purpose.
Or manipulating impulse control.
That's the social engineering angle. Imagine a hacker dialing down your impulse control before sending you a phishing email or trying to get you to gamble. They aren't just tricking you, they are physiologically altering your ability to say no.
It effectively removes the user from the security equation. We always say the user is the weakest link, but this makes the user a puppet.
And then there's the financial angle, ransomware.
Oh, right. Your files have been encrypted. But instead of files?
It's your therapy. Imagine a Parkinson's patient whose implant is locked by a hacker. The tremors return immediately. The message says, pay 5 Bitcoin to resume your treatment. It's a denial of service attack applied to the human body.
That is incredibly dark. But we have to talk about where this is all going, because right now, most of these devices are fairly local, right? They connect to a doctor's programmer in the office.
That's changing. And this is where all these research papers really intersect. We are moving from local BCI to global BCI. The Internet of Brains.
The IOB, because we didn't have enough acronyms.
The architecture is shifting. We're seeing devices that connect to smartphones, which connect to the cloud. Your neural data isn't just staying on the chip, it's going to a server for processing because the decoding algorithms are getting too complex for a tiny implant to handle.
And once it's in the cloud, it's vulnerable.
Vulnerable and valuable. The sources talk about the privacy nightmare of global BCI. Think about passwords. If your email password gets hacked, what do?
I change it, ideally to something better than password 123.
Right. But you cannot reset your brainwaves. Your neural reaction to a stimulus, your emotional baseline, these are biometric markers that are intrinsic to you. If that data is stolen, it is compromised forever.
And the source mentioned that this data reveals things we might not even want to admit to ourselves: sexual orientation, religious beliefs, deep-seated prejudices.
Exactly. It's the ultimate big data. Companies wouldn't just know what you bought. They would know how you felt when you bought it. They would know your emotional state before you even consciously registered it.
And this is where it gets really, really interesting. The sources also mention brain-to-brain communication. Please tell me we aren't telepathic yet.
We are getting closer than you'd think. There was an experiment mentioned where they transferred sensor motor information between 2 rats.
How did that work?
They had an encoder rat in one location, let's say Brazil, that learned how to press a lever to get a reward. They recorded its brain activity. Then they sent that signal over the internet to a decoder rat in the U.S.
And the U.S. rat knew what to do.
The U.S. rat received the stimulation and knew to press the lever, even though it hadn't learned the task itself. It effectively downloaded the sensor motor intuition.
So downloading skills, Matrix style. I know Kung Fu.
Rudimentary skills, yes. But the researchers are looking at brainets, networking multiple human brains together to solve problems collaboratively.
A hive mind.
A networked consciousness. Imagine a room of analysts where they aren't talking. They're just thinking together. But think about the security implications there. If you are networked with 3 other people to solve a problem, who is in your head?
And if one of them is compromised, are you all compromised?
Exactly. The attack surface multiplies. If a hacker gets into one brain in the brainet, do they have lateral movement to the others?
Okay, I'm sufficiently freaked out. Please tell me the researchers have some solutions. Is there any hope? Or should we just all start wearing tinfoil hats?
No, it's not all doom and gloom. The researchers are very clear that neurosecurity is becoming a priority. They've proposed some fascinating countermeasures.
Like what? What's the antivirus for the brain?
One concept is the DCI anonymizer.
Like an incognito mode for your brain.
Sort of. It's a signal processing layer that sits between your brain and the external network. It filters the data. So let's say you want to use a BCI to move a robotic arm. The anonymizer strips out all the non-essential signals,
Mm.
your mood, your tiredness, your reaction to the song in the background, and only sends the command, move arm.
So it scrubs the data of the personal stuff before it leaves the skull. That's smart. It decomposes the signal and only lets the necessary bits through.
It is. Another solution is anomaly detection, using AI. Basically, having an AI bodyguard that watches your brain's inputs and outputs.
Watching for what?
Malicious patterns. If the device suddenly tries to stimulate your brain with a voltage that is wildly different from your normal therapy, the AI blocks it. Or if it detects that you are reacting to hidden images like that P300 attack, it could alert you. Hey, someone is probing your recognition reflex.
I like the idea of an AI bodyguard. Warning, someone is trying to make you sad. Blocking request.
And then there are the physical safety measures. Simple things, like rechargeable batteries.
Why does that matter for security?
Remember the battery drain attack. If a hacker drains your implant's battery to 0, and it's non-rechargeable, you need surgery to replace it. If it's rechargeable, it's just an inconvenience. And fail-safe modes, hardware limits that physically prevent the device from delivering a dangerous voltage, no matter what the software says.
So hard limits. You can't hack the laws of physics. Even if the code says burn it, the hardware says I can't.
Exactly. We need to build the safety into the metal itself.
So what does this all mean? We're building a quantum internet to make our data unhackable, but we're simultaneously connecting our brains, which seem to be a most hackable device of all.
It's a paradox, isn't it?
Okay.
We are chasing perfect security for our networks, but we're opening up the one fortress that has always been private, the mind.
It really changes the definition of privacy. It's not just about hiding your emails anymore. It's about the integrity of your own thoughts.
And if we connect this to the bigger picture, security cannot be an afterthought here. In the early Internet Web 2.0, we built everything open and added security later. That's why we have so many problems today. We cannot afford to make that same mistake with the brain.
Because the stakes are different.
Completely different. The cost of a breach isn't just financial identity theft. It's the loss of physical and mental autonomy. We need security by design for the human mind.
That is a sobering thought. We are standing on the edge of a world where network and neural are basically synonyms.
And it raises an important question for everyone listening.
What's that?
In a future of brain nets and cloud-connected minds, if an external algorithm, whether it's a medical device, a hacker, or just a social media feed beamed into your cortex, can alter your mood, your movements, or your impulse control, where does the user end and the network begin?
I think I'm going to need a long walk unplugged to think about that one. Thanks for diving deep with us today. Until next time, keep your firewalls up and your thoughts your own.
Stay secure.